Unit 5. Unit 5 is moving into atomic structure and periodicity, and we're going to be looking at specifically electrons and all about how the electrons roam and what their location is around the nucleus, and get into electron configuration, remember periodic trends, all those fun things. We'll be getting into that, but first today we're just going to look at electrons as waves, looking at their wave-particle duality. We're going to look at these electrons and what properties they have when they're treated kind of like light. So here we're going to start with, why do we get colors? And I kind of did this last year. I just want to see if anybody remembers. How do we see a color? Why is a color seen? Anybody want to? Louder, JD? Okay, what happens? Wavelengths of light, specifically, Naira? What does that mean, reflected and absorbed, in terms of electron movement? I don't know what that means. Reflected. We can say it because we know that's what you learned. What does it mean? How do we see the light? Yeah. Yes, and that's what happens. So here I have a ball, and I feel sorry for the people at home because they can't see it. This is, we're going to call a photon of energy. Oh, Rui, sorry. I forgot of all the people to start. I'm really sorry. Hold on, I'm not ready yet. Ready? All right. I'll give you a heads up next time. Hold on. Okay. So I'm an electron of light, right? An electron. And I'm going to absorb, you guys are all visible light. I'm going to absorb some energy from this visible light in a photon, in a packet. It's quantized. It's going to allow me to get to a particular energy level, okay? And its color that I absorb is going to be different depending upon which photon I absorb. So, hit me. I'm going to, oh wow, he really did. This is a process. I'm not going to release it quite yet. So I got this energy. Now I'm really excited. And I go to a higher energy level, right? I went from the ground state to, what's this called? An excited state. I'm super unstable, right? So what's going to happen to me? Can I go up anymore? No. What has to happen to me now? I'm going to release and fall down. It's the process of that release of that photon, of that color, is what we see with our eyes, okay? So when they say we reflect the opposite of what's blah, 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 it has to do with the absorption and release of those photons of light, and different photons will lead to different energy level jumps. So if he sends me, hit me again, he sends me a photon that's bigger than this one, I could potentially go to here. And I would do it in one step. I couldn't do it, stepwise. It's like a full jump. And then I would have a higher energy, okay? If I have a higher energy, how does my energy compare, or should I say color? Let's talk about wavelength. If you have a high energy, how does that relate to wavelength? Shorter wavelength. So the jump from ground state to this second energy level is going to be a shorter wavelength than the jump from the ground state to the first energy level, which is going to be a different color, okay? So that's basically how it works. So you see, when they say reflect, they're talking about the emission of different photons of different colors, okay? So let's get into all this. Thanks. All right, so moving on to these characteristics. These are things you guys have to know. You've got to know wavelength. Wavelength is indicated with this letter called lambda. It's a Greek letter, lambda. And we're going to measure wavelength in a distance. So usually in equations, we need to convert our wavelengths to meters because it's going to help cancel things out. But meters is not really useful because meters are so big compared to the size of light wavelengths that you're going to need to know nanometers. Who remembers that conversion? Nano 9. There is 1 times 10 to the 9th nanometer in 1 meter. So you will need to know that. Just remember nano 9. Back in the day, there was a show called Mork and Mindy. Has anyone seen that ever in like syndication, where Robin Williams was an alien? Oh my God, I'm old. Anyway, he used to say nanu nanu. That was his alien greeting, and he did this with his fingers. Never mind, it's okay. All right, frequency. Frequency is a measure of how many wavelengths pass a particular point in space per second. So the units on frequency is going to be cycles per second, or 1 over seconds, or seconds to the -1. Those are units. They're also known as hertz, but hertz isn't a unit, a cancelable unit, so you'll need to put per second into your equations. But when you dial your radio to 96.7 or whatever, those are frequencies that you're picking up with your radio. It's indicated with a little V with a hat. That's called nu, N-U. It is also a Greek letter, lambda and nu. Speed of light, you probably know from physics, it's 3 times 10 to the 8th. We will round it, especially in multiple choice questions where you don't have a calculator, and we will be taking that calculator away from you after Christmas, so good times, good times. You will need to use this, but you are given this on your AP sheet. And the equations that you need to know, you really are, this one is on the sheet. You don't need to memorize that one. And energy equals frequency times Planck's constant is on the AP equation sheet. And I'll talk about Planck's constant in a second. The equation that's not on the AP sheet, I call it the combination equation, is E is equal to hc over lambda. You don't have to memorize it, but I would, because it makes life a lot easier and it cuts down the amount of work you have to do a lot of times. And this is the equation they make you use in physics. So if you get E equals hc over lambda, get it in your head now. That'll be one less physics equation you have to memorize second semester. Okay? So what is this H, this Planck's constant? Well, you're going to derive it in physics, but basically when people were studying photons and different packets of energy, these quantized packets, the common denominator that kept coming up, regardless of the size of the packet, was this number. So every photon that we have in the world is some sort of multiple of that number. Okay? So you're going to do a derivation of that in physics. It's pretty cool. So that's Planck's constant. And what's important about knowing these is knowing the relationship. So I can do another demo here. Give me 2 people. I've got this telephone cord. Go ahead, Ellie. Come on, Coffee Hannah, come up. So you're going to stretch out, spread out, stretch this out. Now, you're going to hold still, and Hannah, I want you to, with low energy, kind of just make a wave with your arms. You can flick a little bit, like, okay. So she's kind of making a wave there, right? She's very low energy. What can you tell me about the wavelength? Long. Go ahead and do a little bit of a wrist thing, just a little bit. There you go. That's a long wavelength, right? What about the frequency? It's pretty low. Now she's going to make herself tired, and I want you to like really go to town on that. You're going to have to use wrist. There you go. Now we can see what happened to the wavelength. Shorter, and the frequency is higher, right? She's going to get tired because she's exerting what? More energy. So y'all see the difference? Okay, thanks. Hold on. The thing is, when I do it, it gets like crazy. Just don't let it go. Okay, and then this is with the low. And that's your high. All right, that's it. So you guys need to know those relationships between frequency, wavelengths, and energy. Again, sorry people at home didn't get to experience that. So don't memorize, don't memorize. If you want to use this, memorize it. And your constants, both the speed of light and Planck's constant, are always given to you. So let's just do some calculations for practice. Calculate the frequency of light that has a wavelength of 6.7 times 10 to the -5 centimeters. We are calculating frequency from wavelength, so what equation are we going to use? C equals lambda nu. C is the speed of light, 3.0 times 10 to the 8 meters per second. Frequency is what we're calculating. What's our problem, though? It's in centimeters. We have to convert this puppy because we can't put it in the equation as centimeters. For every 1 meter, we have how many centimeters? 100. So if we divide that, what do we get for wavelength? 6.7 times 10 to the -7 meters times nu, and we'll solve for frequency. Notice how meters are going to cancel, leaving us with 1 over the seconds, which is our unit of frequency. So to 2 sig figs, give me that number. The faster you all go, the quicker we're done. What was the first number? 4.5 times 10 to the -14. Can I get a second on that? Yes. That's 1 over seconds, and there is our frequency. All right. Yes. +14? Yes? Yes. Okay. 4.5 times 10 to the 14th cycles per second, which makes sense. You really don't want a decimal. You can't really have a fractional cycle per second. And that's one thing we got to watch out for. Frequency and wavelength can never be negative. Sometimes you're going to put in a negative energy, and the only reason you put the negative in is because the energy, that tells you the energy is leaving or coming. But as far as using that photon of energy to calculate for frequency or wavelength, you have to use the absolute value of it, because you cannot have a negative energy, a negative frequency, and negative wavelength doesn't make any sense. All right? Calculate the energy of a photon of orange light with a frequency of 5.0 times 10 to the 14th per second. So we're calculating energy. What equation do you want to use? We're given frequency. Yeah, this is where that combined equation comes in. Otherwise, you would have had to use 2 equations to solve. If you don't want to memorize it, you can do lambda nu is equal to speed of light, solve for the frequency, and then plug the frequency in there to solve for energy. That's your call, but I prefer to use one equation. All right, so it's 6 point, I always forget the numbers, 6.2, 6.3 times 10 to the -34th joule seconds times speed of light, 3.0 times 10 to the 8 meters per second, divided by, wait, we didn't want to use this equation. We're going to use this equation. I went off on a tangent. Awesome. E equals 6.63 times 10 to the -34th times a frequency of 5 times 10 to the 14th per seconds. So what is our energy? And remember, this is joules times seconds, so the seconds cancel, giving us our final answer with 2 sig figs. 3.3 times 10 to the -19. Can I get a second on that? Yes. Oh, I lost my shoe. Okay. So yeah, that was dumb for me to want to use the other equation. I don't know why, because I was thinking of wavelength. So are we good? We understand plugging in with Planck's constant. It's just a number. All right. Now, look back to number 2. Notice it's a frequency of, this orange photon is a frequency of 5 times 10 to the 14th per second for a photon. A photon. This next question says, calculate the energy of a mole of photons with that frequency. What did we just find the energy of? 1 photon. So how do we find the energy of a mole of photons? Multiply by Avogadro's number. Okay? That shouldn't be tough, because if I said, what's the energy of a dozen photons, you'd be like, oh, multiply by 12, and all's happy. And then I say mole, and everyone turns purple. It's just a number, right? A mole is a quantity. So what did we get for our answer for the last one? So that was the amount of joules for every 1 photon, I should say. For every 1 photon, right? Well, we want the joules for every mole, for a mole of photons. And how many photons are in a mole? 6.02 times 10 to the 23rd photons in a mole of photons. So photons cancel. And to 2 sig figs, what is my answer? So 2.0 times 10 to the 7? 5. 5 joules per mole of photons. Okay? All right. Calculate the energy of a photon of light with a wavelength of 425 nanometers. Now what equation do we want to use? The combined equation. E equals hc over lambda. I see a problem. Do you see a problem? Nanometers, let's convert that. For every 1 meter, I have 1 times 10 to the 9th nanometers. So I get 4.25 times, is it negative 7? Math is hard. Is that right? Or is it 11? Okay, so that's how many meters our wavelength is. So now all we have to do is plug and chug. We're calculating the energy. We have a 6.63 times 10 to the negative 34th joule seconds, Planck's constant, times the speed of light of 3.0 times 10 to the 8 meters per second, divided by 4.25 times 10 to the negative 7th meters. Let's check out our units. Meters cancels. Seconds cancel. What are we left with? Joules. Is that a good unit to be left with when we're solving for energy? Yep. So to 3 sig figs, based on that wavelength we were given. See how much this is like physics? How much number crunching you're doing? I would be corrected and be told this is physics. It's not chemistry. That's what they would say. Chemistry is nothing but applied physics, apparently. All right. So what's that number? Can we get a second? Okay, good. So these are pretty easy, right? Pretty easy calculations. Let's take a look at this one. The energy required to break the oxygen-oxygen bond in O2 is 496 kilojoules per mole. So that's the energy required to break a mole of oxygen bonds, right? Calculate the minimum wavelength of light that can break the oxygen-oxygen bond in 1 molecule. So what would be the first thing to do that would be smart? What is this the energy of again? Per mole. So what do you want to do? Yeah, let's go ahead and figure out how much energy is required to break 1 molecule. If this is per mole, what conversion do I do to get it per molecule? Right, 6.02 times 10. Now, because I have a little foresight here, I'm in kilojoules, right? I'm going to need to go from energy to wavelength, so I'm going to have to plug it into an equation. Should I leave it in kilojoules? No, let's go ahead and convert it. So for every 1 kilojoule, we have 1,000 joules. So to 3 sig figs, what is the energy? This is the energy required to break 1 molecule's bond. And what is it to 3 sig figs? Times 10 negative what? 19. Did y'all get that? Okay. And the units on this is joules. So that's how much energy it requires. So what's going to be the wavelength? What do we now have to do? Yeah, the combined equation. Energy is equal to hc over lambda. So our energy is 8.21 times 10 to the negative 19th joules is equal to 6.63 times 10, what? 24? 6.63 times 10 to the negative 34th joule seconds times 3 times 10 to the 8th meters per second. And we're solving for wavelength. What unit are we going to get wavelength in? Meters. So what is our 3 sig fig metered wavelength? Cross multiply that times that divided by that. (2.11 times 10 to the negative 7). 2.41 times 10 to the negative 7 meters. Yeah, that's a pretty difficult number. What would that be in nanometers? It doesn't say to convert. We could leave it like this, but I just want to show you why nanometers is nice to use. It's 241 nanometers. Yeah, that's a nice number. So that's why they tend to do wavelengths in nanometers. Okay? All right, so that's, if we hit an oxygen bond with that wavelength of light, it's going to break. Okay, so classification of the electromagnetic spectrum. You guys don't need to memorize wavelengths. If we want you to associate a color with a wavelength or a frequency, we'll give you that information. But what you do need to know is the order of the spectrum. So this is the side that's of your low energy. This is your high energy side. Right here is your little visible spectrum, okay? And starting from low energy, radio waves are low, and then we go to microwaves, and then we go to infrared rays right before the visible spectrum, which makes sense because what's the first color of the visible spectrum? Red. So your Roy G. Biv goes this direction, and so infrared is before red, right? And then we get orange, yellow, blue, I forgot Roy G., green, blue, violet. Indigo, no, it's just Biv. There's no indigo, because then we're going to have to do teal, too, if we're going to do indigo. So we've got our violet, and then ultraviolet goes after the violet, and then X-rays, and then your gamma rays from nuclear-like radiation, okay? So you need to know the order. So as we go this direction, what happens to wavelength? Decreases. We know that energy increases. What happens to frequency? Frequency increases. So you will be responsible for that. You could get questions, what has a higher energy, violet, light, or gamma rays? Which one? Gamma, okay? So I could ask you to compare colors or whatnot. So what we have here are some nice little indicators of electrons being moved around. This first one is we're emitting energy. Why is this considered an emission? Who can tell me why? It's dropping from a higher energy to a lower energy level. If an electron is falling to its ground state, it's giving off energy. So if we were to do any sort of energy calculation, we're going to end up with a negative number here because energy is being emitted. Absorptions are going to be jumping up, and that electron needs energy put in. That's why it's a positive energy to make that happen. Does that make sense? Now, thinking about absolute value of the size of that packet, which packet's bigger, the emission energy of this picture or the absorption energy of this picture? Yeah, the emission. Falling from 4 to 1 gives off a bigger photon than absorbing of 1 to 2. Okay? So that sign just tells us direction. Now, you will have to recognize either an absorption spectrum or an emission spectrum. And if we have time, I know last year you got to look at the spectrum and take pictures on your phone. Remember that? You got to see some stuff. Here, the absorption spectrums are always the full spectrum that the electrons got to pull from. So the little pieces of the spectrum, those are the frequencies of light that made up whatever photon was was absorbed. When the electron falls, we see the emission spectrum, and that is, notice how it's complementary, right? So what we see is a combination of those colors when the electrons fall. Y'all have been camping. Have anyone been like in a really dark cave, like down 2-3 feet underneath the miles under the earth, right? It's really dark, right? Like super, super dark, like you can't even see your hand in front of your face dark. In a situation like that, would Warner's blue shirt be blue? Nope. Absence of color, why? the electrons had no light to absorb, right? No energy to absorb, so they have no energy to emit. And so as you start going back up to the surface, if you're in these like caverns, and you know how things kind of are like shades of gray, and you can't quite see color? Well, that some electrons are getting excited. And so you're having a few electrons starting to jump and fall and jump and fall. But it's not until that you have the full spectrum available that you're going to get that color again. Okay? All right, moving on. The Bohr model was the original model of the atom, basically saying, hey, we have a nucleus, and electrons travel in a very distinctive, predictable circular path, right? It has some good things about it. You know, the Bohr model did teach us about electron energy being emitted or absorbed. We got our main studying from the hydrogen atom. Why does all our basis of study happen with the hydrogen atom? Because it's just got one electron, right? With only one electron in there, we can just watch that one electron, and we don't have to worry about repulsive forces of multiple electrons, because the game changes once you get other electrons in there. So anything we talk about when it comes to Bohr or this Rydberg equation we're about to do has to do with the hydrogen atom and only the hydrogen atom. So here it just shows you can have different transitions. Sometimes second energy level is a ground, not necessarily in hydrogen, but ground is just whatever low energy level an electron falls to. It's not always the first energy level. Sometimes some electrons, like the last valence electron in fluorine, that is a second energy level P. That's its ground state. Okay, so ground state doesn't always mean first energy level. The model correctly fits the quantized idea, meaning if I were to jump between those two steps, could I land in the middle of the two steps on the stool? Can I land in the middle? No. That energy that I absorbed or emit takes you to a specific energy level. You can't have a half of a photon or a half of a quanta. So it's important that you know that. So that's the Bohr also taught us that. But the Bohr is incorrect because of what we now know about orbitals, and we'll talk about orbitals after we do this Rydberg equation. So this Rydberg equation we only talk about for hydrogen. If I talk about any other atom in the whole wide world other than hydrogen, you can't use this calculation. Okay, you have to be given the energies at the different levels to find changes in energy. Here, we can actually calculate the change of energy in a hydrogen atom as the electron either falls or absorbs energy. So your sign's going to work out here. If an electron falls from a higher energy to a lower energy, we get a negative because light or energy will be emitted. If the electron jumps, it means it absorbed energy, so we will get a positive. So you can watch and make sure your signs are correct. But again, be careful. If you get energy from this equation and you plug it into something to find wavelengths or whatever, make sure you use the absolute value, because you can't have a negative wavelength or a negative frequency. Don't memorize this. You're going to know that you're going to be given this, and it's n squared final minus n squared initial. It's always final minus initial. And these are going to be whole numbers because, again, we're talking about a quantized system here. You're going to get a number that's pretty much a whole number, and that's what that quanta of energy is that's released or absorbed. So we're only going to do this first one, and then we don't have to really do the next one to answer the final equation. So what is the color of a light emitted when an excited electron in the hydrogen atom falls from 5 to 2? Notice it says hydrogen atom. If it doesn't say hydrogen atom, you can't use Rydberg. Okay? So delta E is equal to negative 2.178 times 10 to the negative 18th. And this is where the joule unit comes from. 1 over, what's my final N? 2. So 2 squared is 4 minus, what did I start? 5. So that's 25. I'm going from 5 to 2. Should my energy be negative or positive? Negative, because energy is being emitted. All right, let's calculate it and tell me to sig figs here, I don't know. Just base it on the constant. That's all you got to base it on. So what is my energy change? And my unit is joules. Okay, now here's what the question, though, says. What color of light is emitted? Any ideas what we need to do? If we go back to this picture, what could we relate the color to? Look at the numbers. What are these numbers? Those are wavelengths in meters. So in order for us to find what this energy light is that we're getting, we're going to need to figure out the wavelength in meters. So let's go back now. How am I going to get from energy to wavelength? And again, we're not going to calculate this one. We'll talk about it, but we don't need to calculate it. How do I get energy to wavelength? hc over lambda. Now, don't put in a negative energy here because you'll end up with a negative wavelength. And it's fine. If you put it in negative, just know that the wavelength isn't negative. And if I get that, I'm going to know you're not thinking. Okay, you got to think. So 4.57 times 10 to the negative 19th joules is equal to 6.63 times 10 to the negative 34th joule seconds times 3.0 times 10 to the 8th meters per second divided by wavelength. So let's go ahead and solve for that wavelength. What do we get? .35 times 10 to the negative 7th meters. So let's go back to our picture. It's pretty much ultraviolet, right? And just FYI, and this is something that we used to have students memorize, anytime your ground state is second energy level, it's ultraviolet light. And that kind of proves it. You don't need to memorize that. But this is UV light, and it falls to the second energy level. Visible light is first energy level. Ultraviolet is second. I can't remember, or I don't know. I can't remember it. I don't even know it. I used to know it, and that might even be wrong. But anywho, based on this number, this is ultraviolet light. Don't memorize wavelengths. We'll give you that information. So let's answer this question. Which transition results in the longest wavelength of light of these two? 5 to 2 or 3 to 2? So the question you have to ask yourself is, which one is going to give off more energy? 5 to 2 or 3 to 2? Huh? Why? Yeah, it is true. Why? Why? It's a longer energy transition, right? So this is more energy. This is less energy. We all get that. If I were to fall from the 10th story of a building versus a first story, I'd probably have a lot more energy exerted on my body when I hit that ground, that impact from the longer distance, okay? So let's relate. More energy is what to wavelength? Small, big. So what's the question? What's the answer? 3 to 2. Okay, so you need to be able to take it to energy, to wavelength, to frequency. You need to be pretty comfortable with those comparisons. All right? And we're about done, but let's wrap it up with a little discussion about what an orbital actually is. So the whole Bohr thing, great start for the world, great start for science. It taught us a lot. But in actuality, we learned we can't know the velocity and location of an electron at the same time. In other words, we can't define a path. Impossible. That is the Heisenberg uncertainty principle. So instead, we've come up with the idea of an orbital. An orbital is difficult to define precisely. It's a wave function, which when you take physical chemistry and beyond in grad school, you can study more of it. It's a picture of an orbital as a three-dimensional density map. So I always use the idea of a ceiling fan. You all have laid in bed under the ceiling fan, and when it's going really fast, it's like a circular shape, isn't it? Okay? It would be kind of difficult to exactly pinpoint where the fan blades are, and especially when it's going super fast, but you can kind of see that shape. And that's what I want you to think about of these orbitals. Three-dimensionally, it's where electrons can be found. And it's actually 90% probability of where you're going to find an electron. The radius of the sphere and the hydrogen encloses 90% of the total electron probability. So when you see pictures, there's all sorts of different representations of orbitals. S orbitals, when you plot their distance from the nucleus and the probability of where they'll be, come up with this kind of shape. So your highest probability of finding an electron is that far from the nucleus. Okay? It's a sweet spot. Here, the way these pictures work, the darker it is, the more likely you're finding an electron. So the more, why is it darker in the middle and it gets lighter as it goes out? Why would an electron prefer to be around here than further out? What? Say it louder? Yeah, the nucleus is positive, right? So there's going to be somewhat of an attraction. So electrons are more apt to be found closer than further out. So you can see the further out you get from the nucleus, the less probability of finding an electron. And here, I mean, why is it low here? Because this is like right on the nucleus. And so it gets to the point, there's just this sweet spot of perfect energy and attraction based on Coulomb's law, positive and negatively charged things. There's a sweet spot. So this is where our highest density is. So this is, and this is distance from the nucleus in its probability versus, oh, this is radial probability versus just random probability. So the further you get away from the nucleus, the less apt you are to find an electron. And here they're doing it like a three-dimensional radius, and they plot it and it just comes out different. Again, this is like advanced PChem. We don't need to really get into it. I just wanted you to see the existence of these pictures. Okay? Because if they show up on the AP, they might be wanting you to talk about them, something, or use them to figure something out. Who knows? So I just got to show them to you. And that's it. Starting tomorrow, we're going to be doing S and P and D and orbitals and sublevels and all that fun stuff. I like tomorrow. Tomorrow will be fun.